Alright, so I think this is recording. We're looking at rational functions. Rational functions are a ratio of polynomial functions. The numerator and denominator of this fraction are polynomials. And we're doing three things. We're finding the domain of this rational function, then examining the domain to the values. If there are any values that are excluded, they will either appear in the graph as a vertical asymptote or as a hole in the graph. So we start out with factoring. Now I'm going to go ahead and factor the numerator, but here I'm the main interest is factoring the denominator. This has a greatest common factor of x, which gives me x minus 1. I don't want to reduce this yet until after I've determined my domain. My domain is a set of all real numbers excluding any values that cause division by 0. X equals 0 and x equals 1, we can see that by inspection that causes division by 0. So we throw those values out of the domain. So my domain is from negative infinity up to 0, excluding 0, and from 0 to 1, excluding 1. Now, if you've excluded values from the domain for a rational function, then in the graph it will appear either as a vertical asymptote or a hole. So we come up and we reduce the fraction. We see that these common factors of x minus 1 divided by x minus 1 is just 1. So we say they cancel. But this x squared divided by x also cancels. So we're left with just an x. Alright, so here the question is that since we had a factor of x that also canceled, we're left in the numerator, or excuse me, in the denominator with just 1. So we don't have a variable left in the denominator, and so both of these are going to appear as holes in the graph, and we do not have a vertical asymptote. So our reduced fraction, the denominator of our reduced fraction, determines that. So we have no vertical asymptote. And we have two holes. And the location of the first hole, well, when x equals 0, if we plug 0 in, it's going through the origin, 0, 0. The second hole, 1, 1. So we know that when you graph this original function, its appearance is going to look like a line, that 45-degree line that passes through the origin. So let's go and confirm that. So if I do need to put parentheses around that, otherwise when I hit my division, it'll think I'm just dividing the second term, and I want to divide the whole numerator by x squared minus x. So yeah, we were correct. It does appear as if it's just the line y equals x, but it's not, because we know that there's two holes in this graph. Even though they're not showing up, the graph just doesn't, the software doesn't illustrate that details, but in the table it does. We see that at x equals 0 and x equals 1, there is no related y value. And if we compare this graph to just the line y equals x that does not have any holes in the graph, and if we look at its table, well, see there it converted it to a table without. Sometimes it seems inconsistent. So I'll duplicate it, then convert it to a table, because sometimes I like to see both the equation and the table. And here you can see that where x equals 0 is undefined and x equals 1 was undefined, here 0, 0, 1, 1, those are points on the graph. And we know that because we know that these two graphs have the same appearance. The original graph just has two holes. It's not illustrated by this picture, but is illustrated through the table. And the second graph does not have the holes. And that's illustrated through the table that it does, that at x equals 0 there is a related y value. And so anyway, I hope that helps.